Thank you to the organizers for the invitation. It's a pleasure to be speaking here today. This talk will be about modeling and exploiting perturbations for causal inference in Gaussian latent variable models. Before I get going, I want to acknowledge my collaborators. Most of the content of this talk is based on a joint paper with Peter Buhlmann. Towards the end, I will discuss some ongoing work with Peter, as well as Juan, who's a PhD student at ETH, and Christina, who's another postdoc here at ETH. So to motivate this talk, I want to talk about an application that I've worked on closely over the past couple of years, and it's that of California reservoirs. The California Reservoir Network consists of about 1,500 reservoirs, and they are a major source of water, and that they buffer against severe drought conditions, which the state frequently experiences, including right now. And they're used for various demands, including hydroelectric power generation and agriculture. The water managers of these reservoirs have to assess the likelihood of system-wide failure, that means multiple reservoirs reaching critical conditions at the same time, as well as the effectiveness of potential policies. Now, the reservoir network is highly interconnected. So being able to assess system-wide failure and effectiveness of policies requires understanding these dependencies. Some of these dependencies may be due to physical connections between the reservoirs, but most typically it's due to coordinated management because of some common demands that these reservoirs are used for. Now, graphical models provide a powerful framework to encode dependencies. So here I have a toy example of a graphical model among 8 reservoirs. Each node represents the reservoir volume of a particular reservoir. A missing edge indicates some conditional independency between the pair of reservoirs, and the strength of an edge encodes the degree of conditional dependence. Now, so you typically learn these graphical models from data, but the challenge that arises is that there are many driving factors of the reservoir system that are latent. So I'm here denoting this latent variable by this node in the cloud at the top. Now, these external factors could be due to weather, economy, politics, some of which may be known, most of which are unknown, either unknown or very difficult to model. Now, to illustrate the significance, the importance of accounting for latent variables, on the left, I have the reservoir network with the latent variables. The dotted lines represent their effect on the reservoirs. The solid edges represent the conditional dependencies between the pair of reservoirs. So this is dependency after accounting for all external factors. On the right is what happens if you marginalize out the effect of the latent variables, or do not account for them. You get these spurious edges that is shown in red. In some sense, these are not real. And what I mean by that is that they appear simply because you've not accounted for all relevant phenomena. And policy decisions based on models without latent variables, the one on the right, may lead to suboptimal management. So when we developed the first statewide statistical model of the California reservoirs, we ensured that these latent variables were included in the model. Our approach was based on an undirected Gaussian graphical model with latent variables, and we used that to assess system-wide risk to various drought conditions. Now, there's much room for improvement for these models, and this has been a motivation for much of my subsequent work methodologically. In particular, the water managers of these reservoirs need to design better policies or good management policies, and that requires making causal conclusions. And as a result, the focus of this talk will try to address some of that and focus on causal inference with latent variables. Okay, so what are causal questions? Causal questions are about the mechanism generating the data or predictions after external interventions. So in the context of reservoirs, it is how does change in one water level of one reservoir affects water levels of the other reservoirs. This is quite important for coordinated management of the reservoir system. And it's also important across many other applications in science and technology. Now, a powerful framework to encode causal relations is directed acyclic graphs, otherwise known as DAGs. These are graphs with directed edges and no cycles. They have some nice properties. The first one is that they encode conditional dependency relationships that can be read off directly from the DAG using deseparation statements. They also provide a concise representation on the underlying distribution of the variables in the network. For example, if the variables are generated according to a DAG, their joint density function can be factorized as the product of conditional density functions, where you need to only condition on the parents of the particular node. Parents are nodes that are directly pointing to the node of interest. This is kind of in contrast to standard factorization of distributions, where you need to condition on all the variables in your order preceding the variable of interest. So you get a much more concise representation this way. And perhaps the most important feature of having DAGs is that they allow you to characterize post-interventional distributions. That is, how does the distribution of the variables in the network change after an intervention? And this is crucial for extrapolating to unseen environments. So given the utility of DAGs, we'd like to find a DAG. They're typically unknown, so you have to learn it from data. So in a nutshell, the objective of this talk is to find the causal relations, the DAG, among the observed variables X with latent confounding H. In other words, I want to identify these solid black edges. Okay, so a vehicle to learn DAGs is to impose some data generation mechanism of the observed variables, and we use a kind of a popular framework of linear structural causal equation models. Here, every variable is expressed as a linear combination of its parents among observed variables and latent variables. So for example, x3 is expressed as a linear combination of x1, h, the latent variable h, and x2. Now you could do that for every node in the system. You can also compactly represent it as I have here, where it may seem a little bit strange because x is on both sides, but it's important to note that b star here, which represents a population parameter, has zeros on the diagonal, and further after some reordering is lower triangular. And b star is an important quantity, why I've highlighted it, because it encodes the graphical structure, namely xk is a parent of xj in the graph if and only if the corresponding entry in b star is non-zero. Now gamma star, another population parameter, represents the effect of the latent variables. Epsilon is a noise term with independent components that's independent of the latent variable. So this is our structural causal model, linear structural causal model. And the goal is to identify B star from the data of the observed variables. Okay, a fundamental challenge that arises is that of identifiability. So even if gamma star is equal to 0, that there is no latent effects, you have identifiability up to a Markov equivalence class. Namely, even if you have infinite amount of data, there could be many DAGs that are equally representative of such data. And hence you cannot, in some ways, distinguish them. So in this toy example here, I have a DAG with no latent variables, a DAG. And there's 7 others in the equivalence class that are equally representative of the data. And you can go from one DAG to another DAG by appropriate edge reversals. Now the situation becomes even harder when there are latent variables, so gamma star is non-zero, and that the equivalence class will be potentially far larger. Now if you start imposing certain assumptions in the underlying model, such as dense latent effects, meaning that the latent variable affects many of the observed variables and that the underlying DAG is sufficiently sparse, then you have identifiability up to a Markov equivalence class. Okay, so the hope is to maybe alleviate some of the identifiability issues, and the way we try to address this is by exploiting what are known as interventions. These are direct external perturbations on the variables that could be affecting the latent variable or any of the observed variables. Okay. And interventions have shown to be quite useful for identifiability. And further, there's a deep connection between distributional robustness and causality, in that if you exploit interventions and perturbations, the model that you find is robust to distributional changes. Now, given the utility of perturbations, we would like to model and exploit them, potentially when their strengths and locations are unknown. And the manner in which we think about these perturbation data is data of observed and latent variables that come from environments or experimental conditions or subpopulations in a set that's denoted by script E. So in the context of reservoirs, what I have here is a time series of a reservoir volume data over time. Perturbations can be viewed as changes in management. And as a result, environments can be thought of as different time blocks in the reservoir data set, where the drought conditions have changed, and as a result, management has changed. So for example, one environment could be the normal period where there's a good amount of rain. Another one could be an abnormally dry period, moderate drought period, or extreme drought period. So in the setting of reservoirs, these environments occur very naturally. And if you have some domain expertise, you can really categorize the data into these different environments. But more generally, you have to potentially use other techniques like change point detection or clustering to determine what your environments may be given kind of a data set. Okay, so now we modified the original structural causal model by making two simple modifications. One is that we are allowing the latent variable H to vary across environments. And the other is that we have an additive noise term, delta, and that these are direct perturbations on the observed variables X. With delta, we assume that it's independent across coordinates. Now, it's important to note here is that changes in the latent variables or some of the observed variables will propagate throughout the entire network. So you expect the entire distribution to kind of vary across these environments. And this really gets at why perturbations are useful for our identifiability. Note that the parameters, the population parameters, B star and gamma star, are invariant across all the environments. So the same B star, same gamma star fit the data equally well across all these environments. So while the distribution of the observed and latent variables is varying, these parameters are not. And this is what you're exploiting. And this is what buys you substantial amount of identifiability, as well as robustness to distributional changes. If you see enough variation of the data and are learning these parameters that are kind of robust across all these different settings. Okay, so compared to related work, what we're able to exploit are perturbations on any response variable of interest as well as latent variables. So previous work are not able to completely exploit these perturbations. And as you'll see in the slides later, exploiting these perturbations can be quite helpful for identifiability. Furthermore, a lot of the previous methods output a single DAG structure and do not give an equivalence class when the underlying model is not identifiable, when there's not enough perturbations. And furthermore, previous work do not directly model the latent effects. And this really becomes important when there is some sort of underlying structure, maybe that the number of latent variables is not very large compared to the ambient dimension. If you do not take that into account, this extra structure into account, you have substantially reduced identifiability and worse small sample performance. So by modeling the latent effects, you do gain quite a bit. Okay, so to develop the estimator and the technique, I will further parameterize the model. I will then write the distribution of epsilon plus delta as a Gaussian distribution with mean 0 without loss of generality, and a diagonal covariance where the covariance is specified by this vector WE star, E because it's changing across environments, star because it's a population parameter. And for simplicity, I'm going to assume that the latent variables is IID with a specified by a scalar parameter psi. Now this IID assumption can be relaxed, but we do this for the talk for simplicity. Now the marginal distribution of the observed variables is specified by these invariant parameters, B star and gamma star, and these perturbation parameters, W and psi, that are changing across environments. Now with that, we can start thinking about an estimator, in particular a maximum likelihood estimator. We assume we have IID data of the observed variables across M environments. And for now, let's assume that we have a candidate set of DAGs that we would like to evaluate how well they fit the data. I will describe in the next slide how one may arrive at such a candidate set. But given this, you can solve the following regularized MLE, which I will step through. This term is the negative Gaussian log likelihood that measures fidelity to data. This term searches over all DAGs in the candidate set to find the one that is the best fit to data. This term just ensures that the B matrix is compatible with the DAG. It encodes the same structure. And finally, this term penalizes the complexity of the DAG, and the particular penalty term that we use is the number of edges in the moral graph of the DAG, which is simply some undirected version of the DAG where you would add an additional edge when there's a V structure. Okay, so there are two tuning parameters here. One is lambda, which is associated to the penalty term on the complexity of the DAG. The other is a number of columns in gamma, and this represents the number of latent variables. Now, both of these can be selected via cross-validation techniques, but of course, it's kind of it's a practical challenge that we do not directly address in this work, but just propose using such cross-validation techniques. Okay, so how do we obtain candidate DAGs? We propose to use a DAG learning algorithm on the pooled data. So take your entire data across all environments and apply one of these maybe algorithms. One is the greedy equivalence search, GES, greedy algorithm for learning a DAG. And the other is to potentially use a two-step procedure where in the first stage you deconfound the latent effects using a sparse plus low rank decomposition. And the second stage, you run the same greedy equivalence search algorithm. Now, how do we solve the MLE? We use an alternating minimization. It's worthwhile mentioning here that if you fix the other parameters, the optimization problem is convex with respect to B. And this is nice because since this is a parameter of interest, at least when you fix the other parameters, you can solve this one exactly or up to any precision of interest. Now, the candidate DAGs that, let's say, after applying GES, may be dense, overly dense. This is because the GES does not account for latent effects, and hence you're going to get these extra edges, and we perform a greedy backward deletion to remove these spurious edges. Now, if you assume a certain structure like dense latent effects, and sparse underlying DAG, then this entire framework that I mentioned, that I described here, obtains B star as one of its solutions asymptotically. Okay. The natural question here is that, maybe we can find one of the solutions. Can the MLE find the population model under certain settings? In other words, do we have identifiability guarantees? And the answer is yes. And we need certain assumptions for this. One is that the number of latent variables in the model is greater than or equal to the true number of latent variables. The second is that the latent variables induce some spurious.
We may have just lost connection to our speaker. Let's just wait a few seconds and see whether
that's right.
Comes back.
Can email him too. Oh, you're back.
Okay, sorry about that. I don't know what happened. The internet is usually good. Okay, so let me, at which point did you guys lose me?
Just a second ago, so
yeah.
I think you're
okay, so it's not as bad.
Yeah,
as
on that slide, exactly.
Perfect. Okay, so I'll just repeat. What we need for assumptions is that the number of latent variables in the model is greater than or equal to the true number of latent variables. The other is that the latent variables induce some spurious dependency. So the left is a bad example because if you do not account for the effect of H, then or marginalize it out. There's nothing that changes about the graph structure. The right example is a good one because if you don't account for the latent variables, marginalize it out, then you will actually get an extra edge between X3 and X4. Now, this is far weaker than a dense latent effect assumption where you want this H to affect every one of the variables. Okay. Additionally, we require two interventional environments where there's perturbations on the observed variables and that the perturbations are heterogeneous enough. There's enough diversity in the data to exploit to kind of identify the model. Now with this, we're able to state the following theorem. So if B-opt is the optimal solution of the MLE in population, under assumptions 1 and 4, we have the following statement. If you search among all of the optimal solutions, the ones that has a sparsest moral graph is uniquely the population model. So again, go through all of the optimal solutions, look at the one that has the sparsest moral graph, that will uniquely be the population model. And this leads to the following corollaries. One is that the regularized MLE, which had the penalty term with the sparsity of the moral graph, is consistent, asymptotically consistent. It's also consistent under linearity without requiring Gaussianity. That's not crucial, but linearity is. And finally, B star minimizes the worst case risk over distributional shifts, further kind of strengthening the connection between distributional robustness and causality and causal models. Okay, so interestingly, there's a few pointers that I want to, there are a few things I want to point out here. One is that perturbations on the latent variables is actually quite useful for identifiability. In particular, in the paper, we kind of precisely show this, that if you have perturbations on the latent variables, you do not need as many perturbations on the observed variables. This really highlights the utility of exploiting perturbations on the latent variables, which many of the previous work was, did not. The other is that modeling the latent effects is helpful. So if no structure is imposed, then two interventional environments are necessary for identifiability. You cannot, in general, have fewer environments with interventions. However, if you impose additional structure, for example, you control the number of latent variables in the model and make it maybe small compared to the ambient dimension, then far fewer perturbations are needed for identifiability. Again, this gets to the point that modeling latent effects is useful, and this is something that also previous work did not do. They just assume that there's no underlying structure, and hence kind of typically was in this setting where you need a lot of perturbations. Okay, so now this is all good. We have identifiability guarantees if there's enough perturbations. So what happens if these assumptions are not satisfied? There's an equivalence class of DAGs in such situations. And DAGs in this equivalence class have the same likelihood score. So in principle, you can determine these DAGs, this equivalence class, by finding the best scoring DAGs using the MLE procedure. We also have a graphical characterization, and it relies, the first statement that I want to make relies on dense latent effects and sparse underlying DAG. And the statement is as follows. The equivalence class is precisely the set of DAGs in the standard Markov equivalence class of the population DAG, restricted to those that if you focus on nodes that have been truly intervened on, the parents of the DAG has to be fixed to be the parents of the population DAG. Again, for those nodes that you've intervened on, you're fixing the parents, you're searching among DAGs in the Markov equivalence class and choosing ones that have the same parents on those nodes that have been intervened on as the parents of the true underlying DAG. This also kind of really demonstrates how just every additional perturbation further refines this equivalence class, ultimately to the point where you have identifiability. Now, if you don't assume any condition on the latent effects, you have equivalence class being a superset of what I've presented here. Due to time issue, I'll just focus on some empirical demonstrations, preliminary analysis on the reservoir data set. So we take the 10 largest reservoirs in California with monthly volume data, and we have 4 environments corresponding to different degrees of drought severity. So normal condition, abnormally dry, moderate drought, and extreme drought. And we obtained the following DAG that's shown to the right. So there's a few remarks that I want to make here. One is that there's some edges that go both direction. This is because this is because there's more than one DAG in the equivalence class, so there's not full identifiability. The other is that most of the edges are between reservoirs that are in similar hydrological area or have similar hydrological attributes, or have coordinated management because they are in the same district or statewide water project. And the model that we obtain has interventions on latent variables in all the environments. This is to be expected because we expect rain or snowpack or temperature, these latent factors to maybe change across environments, especially when there's extreme drought conditions. We also find that there's interventions on 3 of the reservoirs, direct interventions, and they're strongest in extreme drought environment. And if you look at 2014, 2015, in reality, what happened is that one of these reservoirs released a large amount of water to farmers in the south, kind of the drought-stricken areas to help with farming. And the other reservoir released a large amount of cold water for salmon spawning. There was a lack of cold water, too much hot water at the time. And there was kind of a danger of extinction of certain salmon species. So Folsom released a substantial amount of water during this time period. Okay, so I think I'm a little bit out of time, but I just want to just briefly mention some future work of interest. There's interest in developing more efficient algorithms, such as greedy methods. High dimensional consistency guarantees are of interest as well. And in settings where perturbations are expensive, you'd want to be able to identify the underlying model as quickly as possible with as fewer interventions as possible. And there, it's of interest to design active intervention strategies. So the paper I talked about is here, and I'm happy to take questions, and thank you for listening.
Thank you so much for the nice talk, Armeen. I have a quick question. So you said you allow for perturbations on the hiddens. Do you have to assume something about the structure of that? So for example, if you have 2 hiddens, one is like temperature and one is rainfall, like the perturbations, can they be arbitrarily correlated or? That's
a good question. So the simplest statement you make, I guess if I go back to the underlying model. So here I assume IID latent variables. So you have to modify this, which one in principle can. Then the assumptions become a little bit stronger. So now if you assume correlated latent variables, then what will happen is that the number of environments kind of scales with the number of correlated variables in some sense. Okay. So here, the short answer is it's possible. You need a little bit more interventional data to be able to fully identify.
All right, thanks.
I have a question if there's no other questions now. It's about your slide 24 and I guess 23 as well, but you can go to 24 because maybe it's easier. With the edges, where you had like the equivalence class. Yeah, that one. Great. So I actually think here you should have, I think you can direct the edges between EXC and PNF and also between EXC and BER, because they just should follow from the fact that NML is directed to EXC from kind of meek orientation rules. Because if you're assuming that the underlying graph is a DAG, you cannot add a new restructure. So in regards to your slide 23, if you go back just one slide.
Yeah. Oh, sorry.
No, the 23 one. Yes. Yeah. So if you're assuming that your equivalence class is the subset of the Markov equivalence class where the parents are fixed, that's like having like a CP DAG with background knowledge. And you can kind of add some additional orientations that may be implied by
I
knowing the
see.
parent. Yeah.
That's a helpful comment. Thank you. Yeah, I
Sure,
have to look
no
into
problem.
that, but that's quite helpful. Yeah, so I guess you get a potentially a further reduction of the equivalence class than I have here for this.
Yes, I think
Thank
you would
you.
have 2 more orientations, but yes, I can give you some links to.
Yeah, that would be helpful.
Yeah, sure.
I think
No problem.
I'm somewhat familiar with the paper, your paper. I've heard of it, so I can. But yeah, please do send them.
Sure, no problem. All right. We still have 3 minutes, so if there's any short questions that anyone from the audience has, we can.
I have like
May I
one.
ask
Okay, sorry, Georgia.
Dominic, you got your question.
No, Georgia, please.
So I don't work in this field, so I was kind of like surprised by the assumption that the latent variables have to affect at least 2 random variables in whose causal structure we want to learn. Why is that the case? Like, I assume that in the left situation over here, that's right. If your latent variable only affects one of those random variables, if there's no confounding, so you shouldn't have any issues. Am I missing something?
Yeah, that's a good question. So the reason why the left is a difficult scenario is that you somehow cannot tell the difference between the effect of the latent variables and the effect of the observed variables on one another. It kind of boils down to that, in that there is some sort of identifiability issue that comes up because there's, in some ways, if you look at the underlying covariance or precision of the observed variables, you get 2 terms typically, one that is associated with the interactions among observed variables and the other that's due to latent effects. And if you have kind of this scenario where there's only the latent effects only point to one X, what happens is you run into this issue of not being able to distinguish kind of one from the other.
So is it
I'm
more
not saying
about...
that it's required. I'm not sure about how necessary it is. I think in the most general setting, I think it's, I want to say it's necessary that you have, if you want to generically to have a kind of a statement about identifiability, I think you need more than one effect. That situation that I told you should not occur. But sorry,
so
I interrupted.
Is it more about the if I understand correctly, you can still learn the causal structure and the direction of the arrows, but it's more about the you're losing the identifiability of your B matrix.
Exactly. Yeah.
Right, I understand.
Okay. Great. Thanks so much. Let's wrap up. So I'll start sharing my screen.